All right, so I believe I mentioned at the end of class on Tuesday that my goal for today was to work a more difficult problem or two and show you guys how to use MathCAD with the complex numbers and all of that kind of good stuff, because you're going to need to do that for some of your homework problems for sure. So the circuit that I would like for us to analyze is this guy right here, where we have a 4 millihenry inductor. We're going to have an AC voltage source here. Call this Vs of t, and I'll define what that voltage is momentarily. Over here, we have an 80 microfarad capacitor. We're going to have another 4 millihenry inductor. Over here on the right-hand side, we will have a AC current source. So let's call this Is of t. Across the top of those two inductors, we're going to have a resistor. So this is going to be 5 ohms. And then in parallel with our current source, we are going to have a 10 ohm resistor. And this is going to be an example of applying Thevenin and Norton's theorem to an AC circuit. So I'm going to give us a set of terminals to work with as well. So let's call this terminal A, this terminal B, and our ultimate goal is to find the Thevenin and Norton equivalent circuit for this network in the time domain. Okay. So let's say that our source voltage Vs of t is 12 cosine 2500 t volts, and our current source Is of t is 1/2 cosine 2500 t minus 30 degrees amps. So much like any other problem where we have sinusoidal excitation, meaning our sources are sinusoidal signals, we need to convert this circuit into the frequency domain in order to do any analysis. Okay. So I'm going to redraw my circuit, and we are going to replace all of our resistances, capacitances, and inductances with their impedance. And we're going to replace all of our voltages and currents with their phasor equivalents. All right, so let's start with our source voltage. What should the phasor representation of our source voltage be for this particular problem?
Do a dash with
12 angle 0. Absolutely right. 12 angle 0. So 12 angle 0 degrees volts. And what about our current source? What should its phasor representation be?
Zero 0.5 angle, and then you would need that the negative to be positive. I'm just still practicing that part.
So we have a cosine representation, so let's start there, right? So this is 0.5 cosine 2500 t minus 30 degrees. We only need the magnitude part to be positive, and it's already positive, so we're just going to leave that as 0.5. So we're going to take that 0.5, the magnitude, we're going to take that phase angle, -30 degrees, and throw everything else away. So our phase representation for that current is going to be 0.5 angle -30 degrees amps. All right. So we have our voltages and currents converted into their equivalent phasor form. So now let's work on converting all of our resistors, inductors, and capacitors into their impedances. So what is the equation for the impedance of a resistor?
Our impedance equals V over I.
Okay, so generally, yes, but for a resistor, we just, they're in terms of resistance. The impedance of a resistor is just the resistor value itself, right? So a 5 ohm resistor in the time domain is still going to look like a 5 ohm resistor in the frequency domain. So I can put a 5 ohm resistor here and a 10 ohm resistor here because resistors don't change when we convert from the time domain into the frequency domain. What about an inductor? So what is the impedance of an inductor in terms of the inductor value?
1 over L times is it the derivative of the value of the inductor?
So that is the time domain representation, but we need the frequency domain representation, right? So you're saying that V is L di by dt, which is our time domain relationship. What I'm looking for is the impedance of the inductor. And we derived this in class at the very beginning of our last meeting. So the impedance of an inductor is J omega L. And just to go ahead and get this out of the way, the impedance of a capacitor is 1 over J omega C. And this is the same thing as -J times 1 over omega C. Okay. So for our inductor, we have an omega of 2500. It's given right here. And then we need to multiply that by 4 millihenries. So that's 2.5 times 10 to the 3 times 4 times 10 to the -3 is simply 2.5 times 4 or 10. So both of these inductors are going to look like J10 ohm impedances using this equation where omega is equal to 2500. So what's going to happen with the capacitor? One of you guys throw that into your calculator and tell me what shakes out.
Is it 5 to the -5?
So it shouldn't be 5 to the -5. It should actually just be minus J5 ohms. Or at least that's what I got in my particular calculation, right? So if we have 2.5 times 10 to the minus 10 to the 3 times 80 times 10 to the -6. So that's going to be 2.5 times 80.
This is a company which model is based on licensing their delivery. They don't have
Right, Jared, whoever's got somebody talking in the background, would you mind muting yourself for a moment? So 2.5 times 80 is 160 plus 40, so 200 times 10 to the -3, but then we're going to have 1 over that, right? So that's going to be 10 to the positive 3, 1,000 over 200 is 5, yeah. So minus J5 should be our capacitance. All right. So all we've done to this point is really just set things up, right? We've converted our circuit from the time domain into the frequency domain. And just to reiterate, we do this so that we don't have to do all of that terrifying trig like I did the first day that we tried to introduce steady state sinusoidal analysis, okay? We want to be working in the frequency domain because working with complex numbers, while it is annoying, is significantly easier than working with trig functions. Okay. So our goal now is to determine the Thevenin and Norton equivalent circuit for this particular network as seen between terminals A and B. So where do you guys want to start? Thevenin voltage, Thevenin impedance, or Norton current?
Start with the voltage.
Okay, start with the voltage. Sounds good. That's exactly what I did. All right, so I'm just going to make a copy of this really quickly so that we can play around with it, as it were. So finding our Thevenin voltage. So the rules have not remotely changed, even though we're working in the frequency domain. What I mean by that is that the Thevenin voltage in the frequency domain is still just the open circuit voltage across our terminals of interest. So our Thevenin voltage would be found here. This circuit is fairly complicated, which means that we're probably not going to be able to use Kirchhoff's current law, Kirchhoff's voltage law, Ohm's law kind of relationships. I think that we're going to need to use either nodal analysis or mesh analysis. I'm going to choose to use nodal analysis to solve this particular circuit purely because we're trying to find a voltage and nodal analysis directly finds the voltages, okay? So I am going to choose my ground node to be on bottom. And then I'm going to identify my other nodes. So we have a node here. We have a node here. We have a node here in the middle. And lastly, we have a node here on the bottom. Okay. So it looks to me like I have 3 nodal voltages to determine. So I'm going to call this one over here VA, this one in the middle VB, and this one in the middle VC. And we should be able to see fairly easily that if we can find VC, that's the same thing as finding our Thevenin voltage, since the Thevenin voltage is measured from terminal A to terminal B, or between node C and our ground node, okay? So because we have a voltage source, I'm going to have a voltage relationship equation. So my first equation for this system is VA is equal to 12 angle 0 degrees volts. My supernode contains ground, so I do not need to write a KCL equation at node A. Moving along, performing KCL at node B, I'm going to be adding this current plus this current plus this current together. So that's going to look like VB minus VA divided by J10 ohms plus VB divided by minus J5 ohms plus VB minus VC divided by positive J10 ohms. And I'm going to set this equal to 0. Now I'm going to perform Kirchhoff's current law at node C. And so I'm going to be adding this current, this current, this current, and this current together. So starting with the current at the top, that's going to look like VC minus VA over 5 ohms. Then I have the current directed to the left through the J10 ohm impedance. That's going to look like VC minus VB over J10. My current directed down is going to be negative, the current being supplied by that source. So negative 0.5 angle, negative 30 degrees amps. And then lastly, I have my current directed down through the 10 ohm resistor. So that's just going to look like VC over 10 ohms. I'm going to set this equal to 0. And now we're going to solve this system. So I'm just going to put a space for my results here. In order to solve this system, we are going to use MathCAD because I don't want to do Cramer's rule, which is a bunch of matrix manipulation using complex numbers because I'm lazy and it's hard. Okay. So give me just a moment here and let me bring up MathCAD. All right. So because we're solving a system of equations, we are going to have to use a solve block. We're going to use the solve block in much the same way that we did much earlier in this class when we were solving our nodal and mesh relationships using computer algebra tools. Okay, so I'm going to click the solve block button here at the top left under the math tab. And I'm going to have to identify or declare my guess variables just like we did before. Okay. So I have 3 variables, VA, and now I'm going to say that VA is equal to 1 angle 0 degrees. Okay, so I'm telling the computer to expect the voltage VA to be a complex number. Technically, this isn't necessary, but I think it's good practice. Okay, so much like before, I'm going to show you some shortcuts. If we click the operator button here, and we go down to engineering, we can see that this button lets us perform the complex conjugate operation, and it has a keyboard shortcut, Control Shift, open parentheses. Then we have the degrees symbol, which is going to be very important for us. Notice it does not have a keyboard shortcut. Then we have the angle operator. This calls it polar, which has a keyboard shortcut of Control Shift P. And then we have this scaling operator, which honestly I've never used, but it does have a keyboard shortcut of Control Shift U. So since I want the angle operator, I press Control Shift P and I get my angle operator. And now I'm going to put 0. And because the degree symbol does not have a keyboard shortcut, if I type DEG, I'm effectively giving that angle units of degrees. It's very important that you remember to do this. If you don't, all of your angles will be expressed in radians, and it will not look like you're getting the correct answer when you're doing your work. Okay. Outside of this parentheses, I'm going to Shift 8, so I'm multiplying by capital V. Effectively, I'm giving this complex number a unit of volts. The reason why I am explicitly multiplying, so the reason why I'm doing, sorry, let me put parentheses back around that. The reason why I'm not just doing V like that is because sometimes, not always, but sometimes, MathCAD will interpret things in parentheses next to another letter as a function, and I definitely don't want that to happen. I want it to understand that this is a complex number with a unit of volts, and so that's why I'm explicitly multiplying there. I'm going to follow suit, the exact same thing with VB, 1 Control Shift P, 0 DEG multiplied by volts. And similarly, VC will be equal to 1 control shift P 0 DEG multiplied by volts. Okay. So those are my three variables that I'm declaring. Now I get to my constraint equations. These are just going to be the exact same three equations that we developed a moment ago. So our first equation was VA must be equal to, so that's a control equals 12 angle 0 degrees volts. For my second equation, I'm going to have VB minus VA divided by J10 ohms. Okay, so when I'm putting this J10 in, I need to be careful. All right, so the first thing is we can't lead with a J. So we have two options. We could do 1J times 10, and then if I do shift W and control G, that converts that W into a capital omega or an ohm symbol. So that's one way to do it. I find that a little bit tedious personally, so I'm more likely to do it as 10J times ohms. It's actually here very important that we explicitly multiply. Let me show you why. So if I do 10J and then capital W control G, notice that the J became italicized. Effectively, it's lumping that J in as trying to be part of the unit instead of treating it like the imaginary operator, okay? So it's very, very important that we do 10J times our unit of ohms here in order to have MathCAD interpret it correctly. My next term is VB divided by negative J5 ohms. So I'm going to do minus 5J times ohms. Our third term is VB minus VC divided by 10J times ohms. And this is a control equals to 0. And then we're ready for our third and final equation. So we're going to have VC minus VA divided by 5 ohms plus VC minus VB divided by 10J times ohms minus, and it's very important that you put the minus sign outside of the parentheses. MathCAD does not like negative magnitudes for complex numbers, just like your calculator, so we need to put the negative sign out front. 0.5, control shift P, negative 30 degrees times amps. And then our last term is VC, excuse me, divided by 10 ohms is equal to 0. Right. So those are our three constraint equations. Now we're going to tell this to solve it for us. So just like I did previously, I'm going to put a matrix here. So since I have three variables, I'm going to do a 3x1 matrix. Let me just move this down a little bit. So I'm going to have VA, VB, and VC. Shift colon will be equal to find VA, VB, and VC. Press equals, and it has solved things, okay? All right, so I want to look at a couple of things here. The first of which is that the result we got has been expressed to us in rectangular form using I as the imaginary operator. We can make MathCAD give us the answer in the form we want. Generally speaking, I prefer my answers to be in polar form with my angle expressed in degrees. So if I go to this math formatting tab in the top middle with this block highlighted, and I come down here, so this middle section, the bottom right option says 1 + 1i. This is my complex values menu. So this is a drop-down menu that lets me tell MathCAD what my preferred way to see complex numbers is. I have 5 options. Rectangular form with I as the imaginary operator, rectangular form with J as the imaginary operator, like we use here in electrical engineering. Then we can express our answer in polar form with an angle in pi radians, our answer in polar form with an angle in radians, and finally our answer in polar form with an angle in degrees. So this is the one I'm going to click. So now we can see what our answer is. One thing that may seem a little bit off-putting or wonky here is that our VA answer is 12 with an angle of 9.371 times 10 to the negative 63 degrees. That is just MathCAD being a little bit obtuse. Anything to the 10 to the negative or times 10 to the negative 63 is extraordinarily close to 0. So that's its way of fumbling towards 0 degrees. If we played around with our guess values, we might be able to make it say explicitly degrees, but just recognize that that number is incredibly small. So just treat it like it's 0. The other degrees, or the phase angles for the other quantities look fairly normal. Okay? So using these results, we know that our Thevenin voltage is nothing more than VC. So VTH for this particular system should be 12 angle negative 180. So what I'm going to do now is I'm going to go back to our engineering paper and write these results in. So for VA, we got 12 angle 0 degrees volts. For VC, we got 12 angle negative 180 degrees volts, or negative 12. And for VB, sorry, clicked the wrong thing, 65.944. With a phase angle of negative 102.702 degrees. Volts, and VC is equal to VThev. And we can see that here explicitly. The positive polarity terminal is associated with the green node where VC is. The negative polarity terminal is associated with our ground node. So VTH is equal to VC minus 0. All right. So before we move along to other quantities, do any of you have any questions about any of the handwritten work I did here or any of the MathCAD work that I did?
I'm assuming a problem on the test would be something like write the equations out and not solve it, because this is just, we can't do this in the test.
Exactly right. You cannot actually calculate something like this on the exam. So 100% right. If I were to give you anything like this, it would be identify which is the correct equation for node A, B, or C, and I would give you a list of equations. Only one of them would be correct. The others would have small errors that you would need to identify.
And could you scroll up to the original circuit drawing, what the value was for the capacitor?
It's 80 microfarads.
Thank you.
Mhm. All right. Anything else before we look at either the Norton current or the Thevenin impedance?
No, I think that was Dave that asked a better version of my question. So thank you, Dave, or whoever that was.
All right. So let's find the Norton current next. So I am going to paste my circuit here. And once again, I'm sorry, cutting off this 5 for whatever reason. Probably because I didn't copy it well. Our Norton current is determined by shorting out our terminals and finding the current flowing through that short. Okay. So I am going to elect to use mesh analysis here. Mainly because I'm trying to find a current. Really no other reason than that. And also I would like to do mesh on MathCAD. It's not going to be particularly different than how we did nodal, but I'd just like to be able to show you an example of it. So I'm going to label my mesh currents. So I'm going to call this mesh current I1. This will be my mesh current I2. This will be my mesh current I3. And then this will be my mesh current I4. So the reason why I'm drawing my mesh current I4 around my 10 ohm resistor is because that 10 ohm resistor is shorted out by the short circuit to the right of it, which means I know for a fact no current will flow through it. So if I included it, I would just really be adding extra equations that are going to cancel each other out. So it's literally not any use to us whatsoever to include this 10 ohm resistor in our work here. So I'm eliminating an equation from our mesh network by using simple observation techniques to realize there's not going to be any current flowing through it. All right, so I have a current source, so I'm going to have a current relationship equation. So that's going to look like 0.5 with an angle of negative 30 degrees amps will be equal to I4 minus I3. Now I'm going to write my KVL equation around my super mesh. So I'm going to identify that really quickly. Let me do this in gray. So this is the path that I'm going to take. So my super mesh is between meshes 1 and 3. So I should be combining these two meshes together. Like so. Great. So the first thing that I see is my negative J5 ohm resistor or capacitor. I'm following I3 at this point of the super mesh. So this is going to look like I3 minus I1. Then I see my J10 ohm inductor. This has a current of, the J5 or the negative J5 should be I3 minus I2. I got ahead of myself. My apologies.
Okay, yeah, I was wondering.
Nope, that's my fault. I'm surprised I managed to catch it. The J10 is going to be I3 minus I1. And then I just have short circuits. So I set this equal to 0, right? There's no voltage drop across this part of the short. There's no voltage drop across this part of the short, and I'm back down to the bottom terminal, okay? Now I am going to need to write a KCL equation around mesh 1. So that's going to look like 5 ohms times I1 plus J10 ohms times I1 minus I3 plus J10 ohms times I1 minus I2. Set this equal to 0. And then lastly, I have my KVL equation around mesh 2. So that's going to look like negative 12 angle 0 degrees volts plus J 10 ohms times I2 minus I1 plus negative J 5 ohms times I2 minus I3 is equal to 0. Just to be clear, since I made a silly mistake on the first KVL equation, anybody noticing anything that doesn't seem correct? I can scroll up so we can see the circuit at the same time too, if that's helpful.
No, it looks okay to me.
Okay. All right, so we're gonna solve this system for I1, I2, I3, and I4. And hopefully we can all see that the current I4 is the exact same thing as the Norton current that we're looking for. So bringing back up MathCAD. I am going to create a second solve block underneath this one. I'm going to declare my variables again. So I1 will be equal to 1 Control Shift P 0 degrees units of amps. And I'm going to do that exact same thing for I2, I3, and I4.
Are we going to be needing to do this for our homework assignments?
Yes. There are some homework problems that will require it, and there are others that there are ways to do it without using MathCAD, but they are incredibly tedious. And if you would like, I can take a look at your web work assignment after we finish this example problem up and kind of let you know which ones I think MathCAD would be most appropriate for. All right, so now I'm going to put in my equations. So the first of which was 0.5 angle negative 30 degrees amps is control equal to I4 minus I3. Then my second equation, I have 5 ohms times I1. This is another instance where I think it's very important that you explicitly multiply, or else MathCAD will be weird. Sometimes things are functions when they shouldn't be. Plus 10J ohms times I1 minus I3. Sorry, when I wrote my notes down for this, I did the KCL equation around mesh 1 first, so that's why they're going to be in a little different order than when we did the handwritten solution a moment ago. Apologize for any confusion this might cause. And then plus 10J ohms times I1 minus I2. Control equals to 0. So again, this is the KVL equation around mesh 1. I'll do my super mesh equation now. So negative 5J ohms times I3 minus I2 plus 10J ohms times I3 minus I1 is equal to 0. And I need to make my solve block a little larger to take into the account the last equation. So that was my super mesh equation around super mesh 3, 4. So now I need my KVL around mesh 2. So that was the one that was -12. Hit Control P instead of Control Shift P, excuse me. 12 angle 0 degrees volts plus 10J ohms times I2 minus I1 plus -5J ohms times I2 minus I3. Control equals to 0. And now we can solve this system. So I'm going to put a 4x1 matrix. I1, I2, I3, and I4. Find I1, I2, I3, and I4. And we have no solution found. All right, so let me double check these equations really quickly here. Actually,
Your I4 is not being multiplied by A at the end. There's not a, yeah.
let's
don't know.
see if it does it. Nope, that didn't fix it. So that first one looks okay. 5 ohms times I1 plus J10 times I1 minus I3, J10, I1 minus I2. Okay, then -5J I3 minus I2 plus 10J I3 minus I1 is equal to 0. Okay. And then -12 angle 0 volts, J10 I2 minus I1 minus J5 I2 minus I3. Okay, all my equations look right. So now, since this is saying it can't find it, try changing the gas value or the value of the TOL. So let's just change these to 2. This is frustrating.
What about changing the phase angle from 0 to a positive integer? Or that would change the solution, wouldn't it?
Right, yes. So actually it shouldn't. If we change this from 0 degrees to 10 degrees, that shouldn't change the solution because those are just guesses. What isn't it caring for my guess values? Because this is a system, 4 equations, 4 unknowns, everything is well defined. It should be able to solve this.
What if you say 2 angle 0 times degrees?
That shouldn't matter because I didn't have to do it before. So it's,
yeah, okay.
So sometimes I'm trying to think of what can make this wonky, because it's not saying, like, there are a lot of different errors that MathCAD can give you. So it can say, like, this one is no solution was found, so try changing your guess values because there's something about the guess values that I've selected that it doesn't like. Usually changing one of them is enough. Others will be units aren't compatible. I've seen it do some stuff to where if I had a misplaced parentheses, it'll give me a weird one, but I don't see anything there. So this one is just being finicky.
I'm just being nitpicky. Just I don't know, kind of guessing that your 0.5 angle -30 DEG, that's not blue and the other ones are. That you might not be interpreting that correctly.
Fair enough.
And then you have a negative 12 angle 0 degrees on your last constraint there.
Yeah,
But
I don't know.
could you use the symbol maybe?
Yeah, let me try that just to see. It shouldn't necessarily need it, but at this point, it's embarrassing that this isn't working, so I'm willing to try anything. Actually, it would be the operator menu, and then we need the degree symbol. And then for 12 angle 0, that's literally the same thing as just negative 12. Still not
Dang.
what I'm doing. This is frustrating. Looking to make sure I don't have any odd parentheses here.
I guess you could like wrap all of your like multiplicative statements in parentheses to force it to interpret it that way. So like parentheses around 5 ohms times I1, and then around that whole statement, plus parentheses around 10J times ohms times I1 minus I3. That would be a lot though.
Yeah, I don't think that's the issue. I'm going to play around with the guess values, and worst case scenario, I have an alternate plan. It's still being difficult. All right, so what I'm about to do literally shouldn't make a bit of difference whatsoever. But what I'm going to do up here, oh, that's the wrong one. I'm going to say that ZL is 10J ohms. Sometimes doing this works. And this is, oh no, I need this to be outside of this solve block. Maybe I need to shift this down one more thing. So effectively, I'm going to declare my impedances kind of like global variables.
Mm-hmm.
Five. All right, so right here, this would be a ZR1. Let me bring that find thing back here, just so we can see at what point this works, if it does. Still being ridiculous. Nope, still being ridiculous.
What about your 12 volts there on the bottom? Can you pull that volts inside the parentheses?
Yeah, I mean, I could literally just call this negative, sorry. Negative 12 volts,
I'm gonna do the same.
what negative 12 angle 0 is. But it's not.
Do you not need the 1x4 matrix C in front of the find?
So the 1x4 matrix is just to store the variables outside of the solve block, which I don't really need to do here. I'm just trying to get the dumb thing to solve currently. I'm not sure for what reason it isn't solving. Makes me feel
Okay.
like a jackass, but it is what it is. Because I believe my syntax to be correct everywhere. I believe that my equations are correct as well.
Because right now we should expect to see I1 equals 1 angle 0. Is that correct? And so on down to I4.
Not necessarily. We should expect it to give us a solution.
I see. Okay.
So it should be I1 is equal to something. Actually, because of the default settings from MathCAD, it would be some sort of number in polar format instead of, excuse me, a rectangular format, because that's just the way that MathCAD gives you the answer first. But there's something about the initial solutions. Let me try one last Hail Mary thing here, which would be to get rid of this original solve block. Nope, no interference kind of going on there. Well, all right. So while this is frustrating, it does remind us of something. If we can find the Thevenin equivalent impedance, we should be able to find the Norton current that way, because we have a value for the Thevenin voltage, right?
Yeah. Mm-hmm.
So instead of banging our heads against the wall here, trying to figure out what MathCAD is doing other than making me look like a fool, let's find that Thevenin equivalent impedance. So to find ZTH, we would look at our original circuit. Let me put this 5 ohm resistor back where it's supposed to be. And we need to be looking at a dead network, which means this 12 angle 0 volt source looks like a short. And this 0.5 angle negative 30 amp source looks like an open circuit. So I'm going to go ahead and identify my nodes here. So we have this large red node. Then we have this blue node. And lastly, we're going to have this green node in the middle, like so. So we've already got the blue node labeled as terminal A and the red node labeled as terminal B. So let's make the blue node in the middle BC. And we're trying to find the resistance seen between A and B. And I'm going to be frustrated if this winds up making me use a delta Y transformation, but I have a way around that too. All right, so directly between A and B, I have a 10 ohm resistor. So that's this guy right here. Directly between A and B, I have a 5 ohm resistor, which means that 5 is just in parallel with this guy. That takes care of this. Between A and C, so let's put C down here in the middle. I have a J10 ohm impedance. And then between C and B, so we took that one off, I have a J10 ohm impedance. And I also have this minus J5 ohm impedance path between C and B. So we can simplify this. Let's take care of those parallel connections first. So 5 in parallel with 10 is going to look like 50 over 15. Let me save this and then reopen this program, or it's going to keep giving me that message. All right, so J10 in parallel with J5. So it's going to be something similar to 50 over 15, but the question is whether or not we're going to have a minus J or a positive J there. So J10 times negative J5 is going to look like negative J squared, which is positive 1. So we have positive 1 times 50 divided by J5. Excuse me, yeah, because we add those together. So 50 over J5, and that's going to be the same thing as negative J5, and 50 over 5 is simply 10. Let me throw that into my calculator just to make sure, because that seems to have worked out perfectly for me, but I could be right. So that was 10i times negative 5i divided by mi minus 5i. Yep, negative J10. Okay. Oh, I think I see the problem here. So that is a little frustrating. So the J10 and the negative J10 cancel each other out, right?
Right.
Because they're in series, which means this path
Short.
is a short circuit, which means the Thevenin impedance is a short circuit. So why this math CAD wasn't working is because the Norton current is literally undefined.
What is?
I'm a little
Is it
salty about the textbook I got this problem from, to be honest. That is a mean trick. I mean, I guess a 1 in 75 chance of just picking random problems, but it is a little mean that one of the problems, the solution is the Thevenin impedance is a short circuit, which means the Norton current doesn't exist.
So does that, so if it doesn't exist, does that mean it's 0, or is it literally like undefined? Like, are we dividing by
It's
0?
literally undefined kind of thing, yes.
Oh God.
Yeah. So that's why it can't find a solution. There isn't one.
Huh.
So if we literally changed, let me get my keyboard out here. no problem finding a solution if we change one of those imaginary impedances. So it's because when we do our Thevenin equivalence, or excuse me, when we find the resistance, because the positive reactance of the inductance cancels out the negative reactance of that inductor in parallel with the capacitor, is why that Norton current wasn't coming out to be anything. It's because it's literally undefined.
So like what would happen if I were to like wire this up on a breadboard? Would it explode, or would just nothing happen? Or like, I guess it's hard for me to wrap my head around what it would happen.
Right. So it just means that the Norton current doesn't exist. Like, so the Thevenin voltage is a thing. Effectively, it means the equivalent circuit. Sorry, let me draw this. The equivalent circuit for this thing is just a voltage source.
Ah, okay.
A voltage source in series with a short circuit. Right.
Mm-hmm.
So
Okay.
even if you wanted to try to set this thing up and measure the Norton current, you would need access to a current source. That would still technically be possible. And the reason being is that real voltage sources and real current sources have characteristic impedances that would perturb the system slightly away from that undefined operating point. So you wouldn't blow anything up or anything like that. You'd probably just get very odd behavior. So
Okay.
with the ratio of V Thevenin to I Norton approaching 0, that means that I Norton must be trending towards infinity in a practical circuit.
Right. Okay.
Yeah. So I feel slightly vindicated in as much as our Thevenin impedance result came out to something that made the fact that we weren't able to find the Norton current make sense. So it wasn't me putting things into MathCAD incorrectly, but I also feel bad that the example problem I randomly chose worked out to a state where there was no solution for one of the steps. So what I may do, and I don't want to tie you guys up for anything, I might find another example problem and just re-record this bit going through all the steps for something that I'm sure works ahead of time. But the steps that we carried out were all correct. Our use of MathCAD, again, was all correct. We just chose the exact wrong problem to find the Norton current for. So, all right. So I said earlier that we would look at web work so that I could give you some hints / suggestions as to what appropriate circuit analysis techniques might entail. So let's do that really quickly. So let's look at homework set 20 and probably 21 as well. All right, so for this problem right here, MathCAD is entirely overkill in my opinion. So my way to approach this particular problem, I'm thinking of a couple of different ways here. One way could be to find the voltage at this node because it's the only unknown voltage in the circuit if we make the bottom our ground. If we find this voltage just using algebra, then that voltage divided by 5 ohms gives us I2. That voltage divided by J5 ohms gives us I3. And then applying Kirchhoff's current law at this node tells us that I1 is simply equal to I2 plus I3. So that's one fairly straightforward way to do it. Another way that we could think about it would be to lump all 3 of these impedances into a single equivalent impedance. Vs divided by that equivalent impedance would give us I1, and then we could use current division to find out how much I1 splits up among the 5 ohm path and the J5 ohm path. We could do a source transformation on this practical voltage source here on the left, giving us a current source in parallel with minus J5, in parallel with 5, in parallel with plus J5. Use current division to find out how much is flowing through the 5 ohm resistor. Use current division to find out how much is flowing through the J5 ohm resistor. Add those two currents together to get I1. Doing that source transformation thing as well, we would have a current source in parallel with those three impedances. So we could use Ohm's law to find the voltage drop across everything. That voltage divided by 5 ohms is I2. That voltage divided by J5 ohms is I3. And once again, I2 plus I3 is equal to I1. So 4 different ways that we could work this off the top of my head, none of which involves actually setting up a system of equations. Problem 2 here. Again, I believe MathCAD would be entirely unnecessary. So how I would work this problem personally is to set up a KCL equation at this node to find the voltage at this top middle node, because every other voltage is a known quantity, right? So we would have this voltage minus Vs over J5 plus this voltage minus 15 angle 90 over J3 plus this voltage minus 20 over minus J4 is equal to 0. Solve for that voltage. And then the current I1 would just be Vs minus that voltage over J5. And the current I2 would be this central voltage minus 20 over minus J4. So I think KCL at that top middle node is by far the easiest way to work this particular problem. This guy right here, it's trying to throw you for a loop because you're told that the current is an exponential form complex number. You can literally treat this exponential form complex number as a polar form complex phasor, so 100 angle negative 73 degrees, and then do everything like we've done previously. When you're finding Vs, it's expecting it to be this form. So whatever polar complex number you get, you would just have Vm e to the j 40t minus theta v. With regards to analysis, since you have IC, you could find the voltage drop across the capacitor. That's the same voltage drop as is across the resistor. So add the capacitor current plus the resistor current to get the current flowing through the inductor. And then the inductor current times the inductor value, or the inductor impedance, excuse me, plus the voltage drop across the capacitor is equal to Vs. So this one is just literally trying to trip you up by using this particular form. Treat this as if it were 100 cosine 40t minus 73 degrees and do the exact normal circuit analysis techniques that you would. Problem number 4 here. You're trying to find this voltage V2. So the first thing that I would do is I would combine this J3 ohm inductor in parallel with this minus J5 ohm capacitor to make it a single impedance between this node and this node. Then I would probably do a source transformation on this guy over here. And then I could do KCL at this node to give me V2 directly. I could also do a source transformation on this left-hand practical voltage source, or excuse me, practical current source, and a source transformation on this right-hand practical current source, which would give me a single loop circuit. I could find the current flowing through the entire loop, and then the voltage V2 would be the current times the 6 ohm resistor plus the voltage drop across. It will be just the voltage drop across that practical voltage source on the right-hand side. So that one's fairly straightforward, doesn't need any MathCAD. Let's see, this guy right here is really a Thevenin and Norton problem. It's exactly a Thevenin and Norton problem. So for part A, Find the equivalent impedance of this minus J5 ohm path in parallel with this 10 plus J5 ohm inductance. By the way, that would be the answer for part C. Multiply that impedance by IS to get VOC. And the short circuit current is literally just going to be IS, because if we short out terminals A and B, all of IS will bypass both those paths. So that one's really trivial. All right, so homework 20 does not need MathCAD at all. Homework 21, we have an op-amp problem. So personally, I would view this as a inverting amplifier, which has a voltage gain of the impedance of the resistor, excuse me, negative the impedance of the resistor divided by the impedance of the capacitor. So we're just treating this capacitor as if it were R1 in the circuits that we had already seen. So we find the voltage gain, multiply it by the source voltage, and that gives us our output voltage. You could absolutely apply the three-step process that I detailed in the lecture video, but the easiest way is to identify this as an inverting amplifier and then use those relationships. This is one of the problems that I was mentioning. So using nodal analysis or mesh analysis isn't necessary for this problem, but it will be much less tedious than effectively using voltage division 3 times. So if you wanted to go about the tedious route, lump everything to the right of this resistor R and include this resistor as a single impedance, find the voltage drop over that using voltage division, then put these 3 elements as a single impedance, find the voltage drop across that using voltage division, and then finally find the voltage drop across this last resistor using a third instance of voltage division. Very tedious, whereas if you were to use nodal analysis, it would be much more straightforward, but you would need a computer to solve it. Problem 2 is literally the exact same thing, except all of the inductances have been replaced with capacitances. Excuse me, problem 4. Here we're at problem 4. I know for a fact that this one technically can be solved without using MathCAD. That being said, MathCAD would be much easier. I personally would use a simple mesh analysis to take care of this one. And then problem 5, once again, I believe it can be done without using MathCAD, but using MathCAD and mesh analysis would make this much more straightforward. Let me look at homework set 22 really quickly, just while we're at it. I think this is getting into instantaneous power and all that kind of stuff. So we have a circuit to analyze, finding IR and IL, right? Finding IS and VS given IL and IC. For this one, since you're given the current IC, you can find the voltage drop across the capacitor. The voltage drop across the capacitor is the same as the voltage drop across this resistor. Adding the resistor current to the capacitor current gives you IS. Since you're given IL, this current IR is simply IL plus IS using Kirchhoff's current law. And then you can find VS by adding the voltage drop across the 10 ohm resistor plus the voltage drop across the 10 millihenry inductor. Yeah. So no need for MathCAD there. And then all the subsequent parts of this particular homework set are dealing with what we're going to learn in class on Monday. All right. So looks like homework set number 21 is the only one that you'll actually need to use any MathCAD on. All right. Do you guys want to talk about anything else, or do you want me to let you go for the day?
Mentally, that's enough today.
Fair enough. I absolutely agree, especially because that MathCAD problem is still ticking me off, or that it's not a MathCAD problem, but the fact that that one circuit didn't have a Norton current frustrates me. So, all right. Well, if you have any questions about any of the homework or anything, by all means, feel free to reach out either through text or email, and I'd be happy to help. I would highly encourage you to start studying for your final, which will be pretty darn soon, if I'm not mistaken.
In 2 weeks, less than that, huh?
Yeah, I think it goes. Let me think about this. I think it goes live on Monday the 7th, if I'm not mistaken. So you'll have the 7th, 8th, or 9th to do it. So yeah, it's a little less than 2 weeks actually.
I saw there's some Moodle links for the days after the 7th. I'm guessing after the final, we're done.
That's correct. I just set it up to have all the class meetings because I set it up before I even make the syllabus. So yeah, so after you take the test, you're done. I like to have a couple of days left over for students to plead their case and all that kind of stuff as is necessary. And, you know, for opportunities if needed, letting students maybe go back and try to work some homework problems for extra points or something like that. Because, you know, I'm trying not to be a jerk all the time. But anyway.
And the lowest score of our test is the 15% one for the exams, right?
That is correct. The test that you score the lowest on counts the least, so that you can have a bad test day and still come out with a pretty okay grade. Anything else?
All good here. I'll reach out if I need anything.
All righty. Well, I will see you guys on Monday. Have a great weekend.
Sounds good. You too. Thank you. Bye.